Yes, good afternoon, everyone, everybody. This is Roger. Today in the class, we'll be proceeding towards the second unit in the case of mechatronics. That is solid state electronics. The working of different electrical components and its capacity, the performance, and based upon the situation, what kind of electronic device need to be replaced and its characteristics will be learning in detail in the second unit. Here is the syllabus of unit number 2, that is solid state electronic devices. We'll be having of PN junction diodes, able to learn regarding the diodes, and next the transistors, that is bipolar junction transistors. Bipolar junction is combination of two different transistors, that is NPN and PNP transistors, cascading of both PN junction and NP junction, that is forward and reverse biased conditions implicate the bipolar junction transistor with the three different polarities: FET, diac, triacs, and LEDs. Its working, construction, characteristics, operation modules will be learned in detail. The analog signal conditioning, operational amplifiers. So operational amplifiers and full wave amplifiers and half wave amplifiers, noise detections, so it is filtering. Noise detection is nothing but the filtering strategies and amplifiers which are utilized in additional for better case of operation leads to the filtering. And these will be discussed in detail in the today's class. Going to the chapter goals, exploring of the semiconductors, discovering how the engineer control semiconductor properties to build up electronic devices. So you need to build up, so you need to characterize the new case of circuit system. One could able to know or understand what are the semiconductors and what way these are going to be operated, and indeed to know that the capacity, applications, and its operational modes need to be analyzed. Similarly, characterizing the resistivity of insulators, semiconductors, and conductors, and how the bondings are being developed, usually the covalent bond that models for the semiconductors, understanding the gap between energy, energy gap, and intrinsic carrier concentrations, exploring the behavior of electrons and holes in the semiconductors. So upon mutual interaction, depending upon the band gap, whether the depletion layer increases or decreases, leads to the electricity increment or decrement of conduction or non-conduction, voltage levels, fluctuations, etc. will be learned very much understanding in way. Even the Discussion regarding the acceptors and donors. Those are the impurities in semiconductors, line to control the electron and hole populations using the impurity doping. Understand the drift and diffusion currents. So diffusion currents, that is incrementing or decrementing, that is fluctuations in the voltages and sudden impact on the voltage levels and varying. Decision that is dependence upon the mobility on doping cells. So doping, nothing but adding or addition of the electrical concepts or electrical flux towards the existing semiconductors. And these are the systems and characterizations that we'll be learning in the today's class. Going into the statistics, the name implicates the syllabus, that is, as we have already gone to the unit 2 syllabus, that is solid state electronic devices. We have gone across the functionalities and characterizations and its diagrammatical constructions, different connector connections between the diodes, transistors. You need to build a circuit based upon the demand existing, plays a major role in the case of these solid state devices. So you need to analyze the or build up an complete electrical circuit. We need to understand about the different components of these electronic circuit system. So in that circuit system, we are utilizing these diodes, transistors, field effect transistors, diodes, triacs, and different LEDs for conduction of heat and electricity, connection of heat and electricity, and minimization of the echo effects and voltage fluctuations due to voltage decrease or minute the voltage fluctuations, nothing but the noise predictions for filterings, different connections that are made for operational amplifiers, etc. will be learned in depth in the today's class. Moving on to the concepts of these solid state electronic materials. Electronics materials are characterized into three different groups. First one is the insulators, second one conductors, next semiconductors. The first one is insulators, having the resistivity that is greater than 10.5 ohms per centimeters, implies the insulation capability, that is resisting towards the external inputs, and indeed to compensate that, insulation plays a major role. Coming to best example, even for the power copper wire which is carrying the electricity will be insulated with respect to the rubber material or plastic, that is coated, insulated indeed from the external exposure. Next one is and conductors. Conductors are nothing but the transmitting of the devices, supports for the transmission of the heat and electricity, and the electricity that it needs to carry with a particular voltage, either in incrementing strategy or in decrementing strategy. That control module will play a major role. semiconductors. This also will carry the electrical to conductivity or electrical EMF at a particular voltage levels, which will conduct in the by the charge carriers upon incrementing of the depletion layer. It specifies two different strategies, that is in biasing systems towards the forward biasing system and towards the reverse biased systems. So it indicates the bandwidth capability in the case of increment or decrement, implicate the forward biased system and reverse biased system. So the current conductivity is being taken place towards the positive and negative characterizations that we'll be discussing in detail with respect to a particular topic in depth. Next, elemental semiconductors are formed from single terminal and atom. So the semiconductors which are at an elemental stage, they have been formed from a single type of atoms, but not on a combination or bonding of different kinds of atoms. So compound semiconductors are formed from combination of column 3 and 5 elements or column 2 and 6 elements. So what are these elements? Here column 2, column 3 has been specified. So what are those columns and what are those elements we'll be looking now. So nominally in the earlier days, germanium is the material that is used for electrical conduction in many of the devices. But in the present days, it has been replaced with respect to the silicon very much drastically due to its higher gap energy and even the less in economical accesses and having oxidized to form silicon dioxide insulating layers also even. So it plays is very much less in economical and compared to the germanium it is an very much quick respondent material obtained at an very much less in cost and will be very much less in dimensions also. We can also very much clear that this is the silicon chip even in our micro SD cards, our mobile SIM cards, and even our memory cards also will place in this silicon material. We need to transfer the data or receive the data and even for the storage of the data in that chip. So hence is a quick transmitter and as well as the recipient and next the storage capability device which has been drastically uh, moved on replacing with respect to the germanium which is utilized in the olden days many of the devices, number of devices. But as far as the sizes or dimensions has been considered, germanium is having wide and young dimensions, but silicon is having only the minimal dimensions. Here the column number 2, 3, 4, 6, etc. We have discussed previously in the previous slide. The third column having the materials such as boron, aluminium, gallium, and indium. As far as the fourth column consists of silicon and germanium. Fifth one is phosphorus, arsenic, and antimony. So these are the materials in our shells at an atomic range. We utilizing these materials for electrical conduction, and aluminum regularly will be utilizing for our mechanical components preparations. This phosphorus, arsenic, antimony is also utilized for the layering type of materials, which are utilized for just labeling structures, labeling structures. Boron is utilized for increasing the ion contents in the water molecules. Gallium, indium, related to the polymer characterizations. Gallium and indium moved on to the polymer characterizations. So here, germanium, going on to the fourth column, that is germanium is an olden days material which is having the temperature of 72.59, and silicon is having very much less than density of 28.086, which is very much less when compared to the germanium, and hence the dimensional accuracy is related, or dimensions related to the silicon is very much less than compared to the germanium, and hence the electronic circuits has been converted from this germanium material to the silicon material because of its less in space occupation in the electric circuits when compared to the germanium, and even much more doubling in the operational parameters in the speed of the transferring of this EMF, generation of the EMF will be very much high when compared to the germanium with the silicon material. Coming to the band gap or and energy for each and every type of the semiconductor, here is the material has been given here, and band gap has been specified here. Let's have a look about these materials once. Germanium having of 0.66, silicon, it is having silicon carbide, is a mixture of carbon, and 3 is having 3.26 of band gap energy, electron volts, 3.26 electron volts. Whereas the germanium is having only 0.66, and hence it is tripling, is 5 times more than the germanium operational capability. Yeah, yeah, covalent bond model. How the bonding is taking place between one atomic molecule to the another atomic molecule. In the physical state of the materials, there is nothing but in our physics, we will be able to learn regarding this. There is atomic theory. Atomic theory is by the Niels Bohr, scientist Niels Bohr, and atom that we are expressed with two different bonding structures, that is ionic bond range and covalent bond range. And ionic bond is much more familiar when compared to the covalent bonding. Covalent bonding, when it is very much less in strength when compared to the ionic bond. But in the case of this covalent bond, for the generation, in the case of electricity, silicon diamond lattice unit cell here, place lattice in the sense the 6 different phases, and its structure has been specified with respect to the unit cell, one unit cell, considering only one unit cell, and these characteristics and the structures has been learned in our MMS subject also in second year. 14 different lattice structures, that is Bravi's lattice structures. 14 different types of structures will be existing. There is hexagonal, triclinic, monoclinic, and face centered cubic, base centered cubic, etc. And these structures also recalled as per the in the electronic concepts also here. silicon diamond here itself. So with respect to the type of the material, the bonding will be getting varied when it has been coincided with respect to the another kind of material. So here unit cell comprising of an one unit particularly, and thus unit has been specified with respect to the um, our comparison is with respect to a square column, and hence it is having six different phases, and a cuboid has been considered. And from that, the lattice structures of silicon molecule has been placed, and the bonding variation will be in such a format as indicated in the diagrammatical representation with respect to another molecule. At the corner of the diamond lattice, it is showing four nearest neighbor bonds, similarly initiated here. Four different similar lattices structures. And view of the crystal lattice along the crystallographic axis. So upon visualization towards depth in view, that is, here it is an phase view, here it is an corner view, and considering it is an long statistical view considering the z-axis format, moving continuously. And how this silicon is getting bonded in between one molecule to the another molecule, and with these two silicon to silicon, how the covalent bonding is being taking place. Because if the ionic bonding has been considered, it will be in a strategical way. So it is a permanent basics way, which is impossible to transfer the electricity from the developed state, that is as a source point, to the different destination points. So hence, we need only the covalent bonding, which will be having only at the time of transferring zones, the bonding need to take in place, and at the different connections, that is diversions, it has to be again split into the two different molecules and to transfer the 2 volts of electricity at that particular T junction towards uh, splitting its electricity from towards the left and towards to the right, that is splitting equally to two different substations. So hence 10 volts of electricity is being considering here, 10 volts of electricity is being passed from the source point, and when it has been transferring here, considering from here to here also there is another subway. Here it is one way and here it is one way. And where are 10 volts? So by splitting it, 5 volts will be distributed towards this, and 5 volts will be distributed towards the another system, another destination point. So hence, so splitting will be getting commenced only in the case of this covalent bonding. But ionic bonding in the sense it is having much more strength which cannot be deviated. But here the voltage which is getting generated by an atomic range is sufficient for splitting or cutting off upon the magnetic flux also. We used to learn different laws here, the electronic components, that is atomic laws, Faraday's laws, Fleming's rules, Lenz law concept. So by utilizing these magnetic fluctuations or magnetic flux generations, the covalent bond can be split into the sublimitations and can transfer the electricity from one source position to the different destination points. And here, charge carriers. So here, two different signs plays a major role: electrons and holes. Electrons and holes. So electrons are the charge carriers, and holes are the positive charge carriers. So positive charge carriers is the symbolic representation of this electron carriers shows the positive sign, and holes shows a negative sign. Sorry, positive sign, and the electron shows with a negative sign. That is zero with respect to the hole, and next electrons and signs. So upon collision of this both the molecules, positive and the negative, upon collision it creates the high amount of positive. So generation of these electronic items upon this coincidence in the bonding covalent bonding development between these electrons and holes leads to a generation of this EMF, and that EMF at what range has been developed will be identified in the form of a voltage and stored in the form of capacitor. Looking at here, near an absolute zero, all bonds are complete. Each silicon atom contributes one electron to each of the four bond pairs. So four different bond pairs, each will be supplicated. So considering this, so one supplication and one pair and third pair and fourth pair. So upon increasing the temperature, adds the energy to the system and breaks the bonds in the lattice. So we are already aware of this crystal lattice, which is having the covalent bonding, maintaining a different structure. And but that particular structure will be getting disturbed by the coinciding or bond breakage depending upon the electron hole combination or collision or an integration we will be calling as electron hole pairs. So those will be getting generated a charge. EMF will be getting generated that will be calling as a charge. This charge will be getting identified. What is meant by this carry? That charge need to be carried and need to be stored, and how we will be calculating that based upon the given input. So for that it has been subclassified into two different strategies. That is intrinsic carriers concentration and extrinsic carrier concentration, right? And moving on to the intrinsic carrier concentration, the density of carriers in the semiconductor is a function of temperature and material properties. So the type of material and the consideration of its properties, nothing but heat and electricity, strength, stiffness, ductility, malleability, etc. The material properties, and at range of temperature it can be resisted. Will be getting identified with respect to the formula Ni square is equal to BDQ expression of minus Ez by kT centimeter per minus 6. So where Ez is a semiconductor band gap energy in electron volts, K is the Boltzmann constant, and the value of this Boltzmann constant is 8.16 into 10 to the power of minus 5 electron volts per Kelvin. T is an absolute temperature in Kelvin. B is the material dependent parameter, that is 1.08 into 10 to the power of 31 per centimeters by centimeters over 6 for silicon. Band gap energy is very much minimum when compared to the free electron by breaking the covalent bond in the case of the semiconductors. Moving on to the schematical structural view or graphical representation towards the temperature and intrinsic carrier density. And this electron density for intrinsic material, and compared that n is equal to Ni. This intrinsic refers to the properties of pure materials. It is pure silicon or pure germanium or pure gallium arsenide. So when germanium, in the case of germanium, the density it is very much high when compared to the silicon. That is depending upon the type of material and its properties that just we have been lying here. That is depending upon its temperature and material properties, right? So maximum temperature, maximum density it is having with the germanium, but temperature it is limited towards to some extent. And when compare the silicon material as a long resistor material having the less density and high charge carrying capacity. Here it specifies that where we already aware of this semiconductor gap in an electronic voltage, it is 1.12 in the case of this silicon, and germanium it is only 0.66. When two different molecules has been in contact, it is a bonding range, that is gallium arsenide. Gallium is a different material, arsenide is a different material. Upon combination of this gallium arsenide, it is having a band gap of 1.42. But in the case of we are considering only the pure materials, coming to the point of this germanium, either germanium or silicon. And compared to the germanium, silicon, they are having the band gap which is very much more. Yes, electron hole concentrations. So what will be the situation that is being taking place in the charge when a vacancy is left and a covalent bond is broken? The vacancy is nothing but an hole. It is a recipient. We'll be calling as an universal recipient in the case of this electronic concept. So the universal transmitter it is an electrons. Coming to the point of vacancy, it is hole. It accepts the electrons. When the bond get broken nearby, it holds the current, and that valency is filled by an electron from a nearby broken bond, and hence its density is represented by P. For intrinsic silicon, N is equal to Ni, that is equal to the density will be P. The product of electron and hole concentrations, the product that is P into N is equal to Ni square. Because N is equal to Ni, P is equal to Ni. Hence, Ni into Ni that is equal to Ni square. Hence, the PN product holds the semiconductor is an molecule. Moving on to the drift current. So, what is meant by drift? Electrical resistivity, that is O, and its reciprocal conductivity sigma. When it is a current flow in a material, when a current is flowing in a material, the electrical field is applied at that particular point, and the field will be getting variated or disturbed to some extent. The charge particles at that point, the charge particles move to a particular extent. That is called a drift, a slight disturbance that is being done when the current that is being transferred in a material. It results in the drift current. The produced current at that particular strategy when the disturbance creates and the transmission of the electrical field is nothing but a drift current. So it is specified with an equation that is just drift current is denoted with this J, that is the Q into the voltage developed, charge into Q is the charge density, and V is the velocity of change in an electric field, and its units are in the area per centimeter square, amperes per centimeter square. Coming to the point of mobility, at low fields, carrier drift velocity is proportional to the electrical field. So, mobility in the sense whether it is feasible or whether it is unconductible with respect to the generating voltage to the drift velocity or drift voltage or that is being generated only at the particular spots. You need to identify it and comparison alignment will be taking place. And hence this mobility refers to the proportional drift velocity. When it is proportional to the electrical field, constant proportionality develops the mobility. Identification is denoted with respect to mu. And these universal recipient considerations, that is holes, recipients arresting the electrical electrons in it, hole mobility is less than the electron, since the hole it holds the current and results in a multiple covalent bond destructions. Right. Going to the velocity and saturation. Electrical field, at what range of velocity the charge is being moved as per the material has been considered. So here they're taking as an completely alone materials, that is unique materials, either silicon specified here and germanium specified here, and the gallium arsenide electrons. So considering electrical field that is generated when per voltage per centimeter towards the x-axis, and carrier drift velocity related to the
Hey,
voltage
sure,
developed towards the
sure.
y-axis.
Hey, hey, hey.
Right. Here, the silicon strategy, it is constantly or linearly increasing when compared to the and stabilizing to a maximum extent. And at the maximum extent, it is being stabilized towards the at a particular point with respect to the wider mouse. It is maximum drift velocity generation and maintains the constant mode at that particular range. Then, when this germanium has been considered with respect to silicon, a previous material before this silicon utilization, that interrupts the voltage increment linearly, and even later on, stability also will be maintaining in a breakage of the voltage, right? Breakage of the voltage. That is very much less when compared to the silicon. Upon incrementing of the voltage, the drift velocity need to be increased. But when compared to the silicon, it is very much less and even stabilizing. And the combinational strategy, that is gallium arsenide, the electron charge carriers and the electrical field generates, the velocity is being increased, and even at a particular point, at a maximum point, at a peak point, it will be getting decreasing simultaneously to a minimal extent. So doping is nothing but increasing of the velocity or adding of an atomic particles by single, indeed to increase or the impurities or add the some of the impurities or purities towards the particular material. And it is a process of adding very small, well-controlled amounts of impurities into the semiconductor. So here the materials, either silicon or germanium, we are utilizing as an semiconductor. The addition of need to change the electrical capability in the semiconductor, the doping plays a major role. Here even it's the process of adding small, there is only of one unit of atom, one atom by one atom also can be added. That's why we are calling it some very small, well controlled amounts. It enables the control of resistivity and even other impurities in wide range of values. As you have been seen in the periodic table, there is 3 and 5. Silicon impurities also verified in the numeric value in that periodical table. Looking at here in depthly, boron in the column 3 has been added with respect to the silicon. Now, an incomplete bond pair creating a valency for an electron. Here, a valence has been created with respect to an boron and associated with respect to the four-side silicon material, and valence has been created. Little energy is required to move the nearby electron into the valency. So hence, the electron will be moved towards the valence. Valence is nothing but an empty that acquires and stores the energy. As the hole propagates charge, it moves across the silicon, and hence this boron molecule that moves towards the silicon, and hence the bonding takes place. So donor impurities, how the donor impurities in the case of this silicon will be verified. Take then phosphorus as in the periodic table in the column 5 has been specified, and a comparison with respect to the silicon. It replaces silicon atom in a crystalline lattice. Phosphorus have 5 outer shells, electron, and extra electron in that structure specifies towards the positive and charge carrying for the charge carrying. And even the material is exhibiting in a still neutral in state, but very little energy is required for free electrons for conduction and not participating in the bond. So will not be deviating this, having 5 different characteristics, and hence this phosphorus has been reconnected with respect to silicon on 4 different sites here, and it is having an extra electron also present 5 outer shells, and it exhibits towards the fifth Li element for its movement, whether in positive charge or even the negative charge, and hence it is being distributing towards the another channel. 4 sides it will be distributing simultaneously as and in the fifth side also. Okay, these are the different uh, Lambdin's elements and properties related to the silicon material, and how the germanium material which we are utilizing frequently in an general purpose electronic components has been replaced with an silicon material for speeding up or speed up of EMF generation and its characteristics improvement, and to analyze the semiconductor characteristics. These are the basics need to be known. That is two cases in the 2 different cases of the semiconductor in the forward bias system and in the reverse bias system. It's working how the working is being propagated and with what changes, and internally what are the implications or changes, necessary changes that are being taking place for the reverse flow of current, reverse flow of charge, and positive flow of charge. We have been just seen as far as its material considered and its properties, the material properties, how it gets varied with respect to the temperature, and temperature to the original properties of the particular material has been analyzed in detail in today's class. And with this data, we'll be having a note towards the depth consideration from the tomorrow's class. We'll be moving
Yes,
on
sir.
in depth towards the concepts of diodes, transistors, and its working and its characterizations in
Sir,
the
you can.
tomorrow's class. Thank you. We'll be moving in the we'll be
Hello,
meeting
sir.
tomorrow's class.
Hello, sir.